Hey, this is a statistics video. It's going to go over Unit 7, Section 3. It's going to concentrate on proportion distribution. So, hopefully, everyone's doing all right. Enjoy. So on Unit 7, Section 3, we're going to concentrate on the proportion distribution. Uh, in Sections 1 and 2, we talked about the X bar distribution, the mean distribution. So this is the proportion distribution, also known as the p hat distribution. So the second type of sampling distribution we will look at is the proportion distribution. Basically, it's a ratio, like a fraction. R is the number of successes, N is the number of trials, and P, without the hat, is considered to be the probability of success on each individual trial. So if we take the number of trials and multiply by the probability of success, and it's greater than 5, and if we do the same thing with the probability of failure, and it's also greater than 5, then the p hat can be approximated by a normal random variable, namely x. But then right here, just pay attention, we have a different calculation for standard deviation. It's a square root of probability of success times the probability of failure, all divided by the number of trials. So we're going to have to come up with our own standard deviation for these. And then continuity corrections, we would take 0.5 and then divide by the number of trials and add that to the right endpoint, subtract that from the left endpoint to get our continuity correction. So here's an example of that. So suppose that a number of trials is 25. We know the p hat interval is from 10 over 25, which is 0.4. 15 over 25 is 0.6. So to convert this to an x interval by performing continuity correction, what we're going to do is we are going to take 0.5. Now, if you remember with an x distribution, so just a regular standard distribution, we would add and subtract 0.5 to either endpoint. But for this one, we're going to take 0.5 and divide by the number of trials. So in this case, we're going to do divide by 25, and that turns out to be, I believe, 0.02. This is a van, and the van. All right, now what we're going to do is subtract that onto the left endpoint that we're interested in. So we're talking about 0.4, and then add it on to the right endpoint, which would be 0.6. So to convert this into an x interval, we're going to actually say that it's from 0.38 to 0.62. Okay, so I'm going to be doing that, I think, coming up, doing the continuity correction. So that's kind of how you perform that calculation. So here's an example. The annual crime rate in a neighborhood of a large city is 111 victims per 1,000 residents. Crimes committed range from relatively minor crimes to major crimes. Apartment building in the neighborhood has 50 residents. What is the population probability P that a resident of the apartment building will be a victim of a crime next year? So that is 111 out of 1,000. So our P is 0.111. Now Q, the not having a crime committed against you, would be 1 minus that, so 0.889. Okay, so can p hat be used to approximate the normal distribution in this scenario? So this is where we're going to test number of trials times probability of success. Is it greater than 5? And then is n times q, is that greater than 5? If both of those are greater than 5, then we can use the normal distribution. So we're talking about 50 residents times 0.111. Is that greater than 5? If you do that on a calculator, I believe you get 5.55. So that is greater than 5. So that's all right there. Now, obviously, if 0.111 is greater than 5, or times 0.111, then 0.889 times 50 would also be greater than 5. I think that turns out to be 44.4 0.045. So yes. Okay, can we use this? Yes. All right, what are the mean and standard deviation? So the mean of this, so the mu, is that 0.111. Now the standard deviation is where we, I highlighted it just a minute ago, 0.111 times 0.889, and we're going to divide by the number of trials, in this case 50. So if you do that on a calculator, it turns out to be about 0.044. Okay? And so what is the probability that between 10% and 20% of the residents of the apartment building will be victims of a crime next year? So probability of 0.1 less than or equal to, now I'm going to write X because I'm going to do this with our continuity corrections. So what I'm going to do is go to my calculator. I'm going to do second vars. We're going to do a normal CDF. Our lower bound is going to be that 0.38. Oh, I'm sorry. No, I have to do that, don't I? I'm thinking of the example before. Sorry. So continuity correction. So to do the continuity correction, we're going to take 0.5. Oh, that's 0.05. And we're going to divide by the number of trials. So in this case, 50. 0.5 divided by 50 is 0.01. So what I'm going to do to this 0.1 and 0.2 is I'm going to subtract 0.01 here and add 0.01 here. So actually what I'm going to do is find the, you're going to see me type into the calculator 0.09 and this should be a 1, sorry. So 0.21. Sorry, should have done a little out of order, but whatever. All right, so on my calculator, second vars, I'm going to do normal CDF. My lower is that 0.09. My upper is the 0.21. My mu is the 0.111. My standard deviation was at 0.044. All right, and then this is going to give me the probability, 0.67, let's say 0.6712. So what this means is that roughly there's a 67% chance that 10 to 20% of the residents will be victims of a crime next year. So pretty good chance. All right, here's another example. The general ethnic profile of a large city is about 42% minority and 58% Caucasian. Suppose the city just hired 56 new employees. It was claimed that the hiring practice was completely impartial with regard to ethnic background. However, only 27% of the new employees are minorities, and now there is a complaint. What is the probability that at most 27% of the new hires will be minorities if the process is impartial and the applicant pool roughly reflects the ethnic profile of the city? So let's get some calculations in here. So we know that the mu is 0.42. Okay. Now our p hat is 0.27. And we should probably throw in here that our q, failure or just not 0.42, 0.58. All right, now let's calculate our sigma. So we're going to do the square root of 0.42 times 0.58, and we're going to divide by the number of trials, in this case 56. So that turns out to be, I'll be back in a moment, square root of 0.42. I got 0.07. Okay. Next, why don't we do our continuity correction? So 0.5, we're going to divide by 56. So 0.5 divided by 56 is about 0.01. 0.01. So now what we're going to do is we're going to calculate what is the probability. Oh, and what I'm going to do is what we're looking for is the 27%. What's the probability that 27% or less, and now I know it says at most, but also or less is at most. 27% at most. So we're looking at, if we're going to, let me draw a little picture here. All right, so what we're looking at is, here's 27%. What's the probability that that's going to happen in this case? So 27 is actually our upper end. So I'm going to add this 0.01 onto 0.27. So I'm going to actually do the probability that x is less than or equal to 0.28. All right, so second verse, normal CDF. Our lower is going to be -1 E99. Our upper is 0.28. Our mu is 0.42. Our standard deviation was 0.07. And so the probability that this is going to happen is 0.023. So the chances of this happening are 2.3%. So what does that tell us? That given the statistics, it's unlikely that out of 56 employees, only 27% would be minority. So maybe it's not as impartial as they're claiming, or maybe there is a problem with the ethnic profile of the city. Maybe it's changed or something like that, but 2.3% chance that only 27% get hired out of 56, given the ethnic profile, is pretty darn low. So something's wrong there. All right. Mechanical press is used to mold shapes for plastic toys. When the machine is adjusted and working well, it still produces about 6% defective toys. Toys are manufactured in batches of 100. Why can p hat be approximated by the normal distribution? What is the mean and standard deviation? So, first, why can p hat be approximated by the normal distribution? So in this case, the probability, now this is going to be kind of backwards, of what we're looking for is 0.06 and then 0.94. So even though defective is not a positive thing, in this case, that's what we're looking at. So the mean is just this 0.06. The standard, the standard deviation is the square root of 0.06 times 0.94 divided by the number that we're dealing with, batches of 100. So let's do that. Second square root, 0.06 times 0.94 divided by 100. So about 0.024. Okay, now why can this be used? So we're going to take the number that we're talking about times the probability of, in this case, being defective. Is that greater than 5? So we get 6 greater than 5. Yep, check. 100 times 0.94. Is that greater than 5? That turns out to be 94. So, yep. So why can? Because n times p is greater than 5, and n times q is also greater than 5. All right. So letter B, suppose a batch of 100 had a 7% proportion of defective toys. What is the probability that a situation like this could occur? And then interpret what it means. So if we take a look at a picture of the standard curve, what we're looking at is that 7%, so someplace here, so, here's 0.06. That's our mu. So 0.07, a little bit above that. So what we're looking for is this area up here. Okay, what's the chance that it's just a little bit above the 6%? All right, so keep this picture in mind. So what we're going to do is a continuity correction. So that's going to be 0.5 divided by 100, which is 0.005. So to change this to an x interval, I'm going to take the 0.07, and since the 0.07 is going to actually be the lower bound, I'm going to subtract 0.005. So what I'm going to actually calculate is the chances that x is greater than or equal to 0.065. All right, so I'm going to go to second verse, number 2, normal CDF. My lower is going to be the 0.065. Upper is going to be 1E99. 0.06 is the mu. 0.024 is the standard deviation. So the probability of this is 42%. So I think we put on here 0.417. So 41.7% chance that 7% of the toys are defective. Pretty good chance. I mean, I don't think that indicates anything's really wrong. In this one, we have 0.11. We're going to use the same continuity correction, 0.005. And again, if we look at what's going on here, here's our mu, right? And we're looking, where is 0.11 in relation to this, right? And to do the continuity correction, that means that we're going to, again, subtract 0.005, which means we're going to do an x interval that is greater than or equal to 0.105. So calculator, everything will basically be the same except for the lower bound, 0.105. So this would only happen about 3% of the time. So as a decimal, 0.0303, or let's just say 0.03. So only 3% of the time would 11% of the toys be defective. So because that's so low, I would check that something is wrong with the machines. That's not going to happen too often. Whereas 7% is, sometimes it will happen, but 3% means something's a little off. And that's section 3. Hopefully everyone's doing all right. Let me know if you have any questions.